All right. So, welcome to our lecture video about demography and sampling. So, for the purposes of those watching, this would be our week 2 lesson. Now, starting with what we're going to be learning today, number one, of course, is the history of demography. And this would be just a brief history of how it came to be. Number two would be sampling or the different formulas used in sampling. And then finally, we have the sampling techniques, the probability and non-probability sampling techniques. So let's begin with the history of demography. So the history of demography is actually quite obscure. Um, many years ago. So it is believed that demography started about 6,000 years ago, where the earliest demographic activity was recorded. So at this time point, we did not even know about what demography is. We simply wanted to find out, or humans simply wanted to find out how many people were living in a certain area. And so the earliest demographic activity that was found and recorded was a census. So if you don't know what a census is, it's basically just a list of the people living in certain households. And back then, the census was just a list of the individuals living in a town. And now, demography was silent for many years after that. And by the way, this would be standard practice in most communities. However, when we finally started demography, was in 1662. So in 1662, John Grant was dubbed the father of demography for his natural and political observations made upon the bills of mortality. So he was a UK based or United Kingdom based demographer. Officially at that time, he was just a statistician. So he was studying how populations were declining and how many people were ready for military service at that time, and how many women were able to bear or are at least able to bear children. So these were all estimates, by the way. So he did not even come up with an exact number. So he simply was estimating the number of military ready men and childbearing women. And the thing about this is that he did it without actually counting the people in a certain age range. What he did was he studied mortality. He was studying the number of people who were dying and the number of people who were being born. So he studied the start and end of life and estimated the number of people in between who were ready for military service and who were ready to bear children. So for his work in the natural and political observations made upon the bills of mortality, he was dubbed the father of demography. And then the latest milestone for the history of demography is now uh, is now the 19th century, where demography just basically became a population centered practice. So, in the 19th century, brought about different populations' needs, and thus demography was adjusted to fit those needs of these certain populations. So, basically, what they're saying is that during the 19th century, demographers were adjusting their practices based on what a population needs. So basically, when a population is slowly declining, they're going to be studying birth rates, they're going to be studying fertility rates, they're going to be studying um, death rates. So there are plenty of things that happened, or there are plenty of different aspects of a demographic population that could be studied. And so when the 19th century came, different problems were arising from industrialization and from the modernization of different industries as well. So what they did was that they adjusted the practice to certain populations. And so there's not really an exact milestone that happened in demography in this time period. It's just basically the transformation of demography into a more population centered practice. Okay, so that's about everything to say about the history of demography. So, how it came to be was that 6,000 years ago, censuses were discovered and it became a continuous practice throughout the years. And in 1662, John Grant was the one who first estimated a certain portions of the proportion, certain proportions of the population, and from that work, we were able to estimate the different age ranges, and then in the 19th century, finally, it became a more population-centered demography. Okay, so moving on to sampling. Now, we've talked about demographies, and now we're going to talk about sampling formulas for the meantime, where it's going to help us establish a minimum sample size as a representative of the population. So basically, what John Grant was doing with his bills of mortality. So he used a certain proportion of the population to estimate another proportion of the population without directly interacting with them. So that is one of the most important aspects of sampling, is being able to take a part of the population and using it to represent the whole. So when we execute sampling or when we do sampling, we have to follow four general steps. Number one is, of course, first define the population from where we're getting the sample from. Number two, determine the sample size. Number three, select the sampling technique. And number four, create the sampling frame. So in this lecture, we're going to be tackling until number three. We're going to do defining the population, or at least we're going to assume a defined population. And then we're going to determine the sample size, which is this portion of the video. And then, of course, we're going to talk about the different sampling techniques that we can employ to actually take the samples from the population. Okay, let's start with our sampling formulas. So these are, in general, the sampling formulas that we use to estimate the minimum sample size. And take note, I do say minimum. So this does not necessarily mean that whatever sample size we're getting from this is going to be the exact sample size. So what we're computing for is the minimum sample size, meaning that you can exceed these sample sizes, but definitely could not go below them. Okay, so let's start with Cochrane's formula. Cochrane's formula was actually one of the earlier versions or the earlier formulas for sampling. Excuse me, one of the earlier versions of sampling that was published, and it was used to estimate a sample size given the estimated proportion of the population with the desired attribute. So this is an estimated value, and from that value we can compute for Q, and we have Z, which is a constant from the Z table. And then we have Yamana's formula. I'm sure you might think that this formula is something that you've seen before. And yes, you've seen this before. And most commonly in modern references, this one's referred to as Slovine's formula. So Slovine's formula is based on Cochrane's formula. So it's a derivation of Cochrane's formula, considering a certain point in its estimation. So basically, Yamanes or Slovine's formula is a derivative of Cochrane's formula. So in this case, we have only the population size and the precision or the significance. So one thing to note in this case is that I've scoured through references and resources, and a lot of the references say that they don't know where, or they could not find any older references that Slovine's formula this formula has been referred to as Slovine's formula at all. So Basically, all of the references, or at least the references I've seen, indicate that this is in fact Yamane's formula, who published the formula, and they could not find how Slovene or this person Slovene to be associated with the formula. So for the purposes of our discussion, we're going to refer to this as Yamane's formula. Okay, so let's start with Cochrane's formula. So again, we have Cochrane's formula over here. You have the breakdown of the different meanings of these variables. Z value based on alpha. You have your estimated proportion that contains the trait over here of interest. And again, this one is an estimated trait. This could be used, or this could be taken from previous studies concerning that population, or previous studies concerning that study of interest. And then Q is simply 1 minus P. And then you have uh, E, which is just your alpha, or the inverse of your level of significance. Okay, so let's have an example over here. You have your 1.96 squared, which again is this one's determined by alpha from the Z table. You have your estimated proportion, which is in this example we have a zero point 0.5. Again, estimated meaning that the researcher determines this. Okay, and then you have your Q over here, which is just 1 minus zero point 0.5, or 1 minus P, which is again zero point 0.5. And then under that, you have your alpha, which is zero point zero 0.05, and then you have your square. Again, if you don't have, or the alpha is not given in the problem, it's always the safest to assume that we're using 95% confidence interval, so we use 5% alpha, or 0.05. Now here is a z table just so that you can visualize where we've taken this value from. So these are the most common levels of significance that we could find, or we typically use. You have zero point 0.1, which equates to 10%, 0.05, which equates to 5%, and 0.01, which equates to 1%. So on a two-tailed test, we have 0.05 at 1.96 over here. So our z value for this example is going to be 1.96. So we have this again, this is just same formula. I've just broken it out earlier so that we can better understand where the values came from. And we input that in a calculator and we get 384.16. Okay, so now again, populations or samples are discrete variables, so they're not supposed to have decimal points. But for the purpose of this discussion, we're not going to round up yet, since there are certain corrections, or there are certain applications that we're going to need to apply to our computed sample size before we apply these rounding up. Okay, so Cochrane's formula offered a correction for smaller populations, and the rationale for this is that a certain number of, let's say, a certain number of samples is going to provide more information if you have a smaller population than a bigger population. So basically, if you take, let's say, 50 samples, or let's say this is our samples, and then you have a population of 100, you're representing about 50% of that population. Whereas if you have a population of 1,000, then you're actually representing just a small percentage of this large population. So, therefore, if our population is small, what we mean by small is less than 5%, or our sample size is less than 5% of the population, then we need to correct for a smaller population. Okay, because if we, for example, if you need a, or if your computed sample size is 50 and your whole population is 100, then you're essentially taking half of the population, which defeats the purpose of sampling. So if we have a smaller population, we use Cochrane's formula to correct for smaller populations. So let me just erase this so I could show you the solutions. Okay, so first, the formula for Cochrane's correction is here. You have your recommended sample size over at the top. And by far, this is the only variable that we've not introduced yet. But this, again, this variable is what we computed for in our last computation. You have 1 plus, again, n0, which is, again, the recommended sample size computed using Cochrane's formula. And then you have the population, which was given here in this problem. So just to substitute the values, you have your n1 or n sub 1 is equal to 385. So we've rounded off n0 divided by 1 plus 385 again, which is again n0 or n sub 0 divided by 1679, which is our population. Okay, when we input this in the calculator, perform the operations, we get 314. So it's a small adjustment of our recommended sample size, but it is definitely something that is necessarily done when we have a smaller population. Next, we can also adjust for unresponsiveness. So sometimes when we do surveys, we don't necessarily get all our surveys back since we don't want to watch our respondents answer their surveys. First of all, that could introduce bias, and secondly, that's going to be very, very time consuming. So our typical practice is that we distribute these surveys in households and we leave them there, then we collect it after. Sometimes we even mail surveys. So this was a practice done way before the internet became such a good media for research. What we did was that we sent mail to respondents, and then we sent it with a pen and another postal stamp. And so they would be giving, or they would be answering the survey, and they would be sending it back at our expense. Okay? So it stands to reason that not 100% of your respondents are going to respond. We're not going to submit the or the response. So we can correct for unresponsiveness for surveys that were sent out but were never returned. So let's assume that only 65% of our population or of our sample responds. This 65% could be taken from previous studies, from pilot studies, from supporting literature. So basically, you can get the response rate. We call this the response rate anywhere or in any source of information. You can even estimate your response rate. Okay. And simply to adjust for unresponsiveness, you use this formula. So n sub 2 is equal to n sub 1, which was computed using Cochrane's correction, and then divide it by the response rate, which is 65%. So it's a very simple formula. It's simple division, and all we have to do now is substitute our variables, and we get 314 divided by 0.65. So you see that I've converted the 65% into its decimal notation, but that's just how it really is in mathematical computations. And we get about 483.07 or 484 rounded up. And this is going to allow us to, despite having only a 65% response rate, to actually obtain responses that are above or at least equal to the minimum sample size recommended. Okay. Next, we have Yamanis formula. Again, this could be referred to as Levin's formula, and in modern references, that's almost always the case. Okay, but if you dive deeper into the literature, you're going to find that a lot of statisticians and demographers agree that they could not find a reference that links this formula to Levin's, but instead Yamanis formula or Yamanis publication. Okay, so we have N, which is the sample size, and you have big letter N, which is the population size, and then you have your E or your alpha, and you square that. It's a very simple formula, and you might notice that this one is a derivation of Cochrane's correction. Okay, so this actually assumes variability to be at a certain point in Cochrane's formula, and so it was set like this. Now, to better illustrate how Slovin's or Yamanis formula work, let's have this sample problem. So, in this case, we have only the given populations: 10,000, 256,000, and 112,675,879. So, let's first set up the first population, 10,000. So you have n is equal to 10,000 divided by 1 plus 10,000 times 0.05 squared. Now, just as a point of information, please do be careful about your squared. Sometimes, and most often than not, I notice that students tend to forget their square. Okay, so be careful in computing manually that you might forget the squared on our alpha. Okay, so it's a very basic formula in which we just substitute the population, and then you have your alpha, and then you square your alpha. So applying the same concept with this with the other two sample problems, you get this and then this. And then of course, let's start by solving the first problem. You have 384.61 or 385. Next problem is 399.37 or 400. And then you have 399.99 or also 400. Now, the reason why I placed this sample problem, 256,000 and 112 million, is that I wanted to illustrate that at 0.05 alpha or 5% significance, you're going to notice that the maximum number of samples that we can actually obtain from a population, no matter how large, is going to be 400. So that's one of the limitations of using Yamanis formula. So at 5% significance, it's capped at 400. Okay? Now this is just a flow chart that I've used to help better understand how we use or implement the formulas for sampling. So first you have your population, and then you could either do, this is again a choice of the researcher though, but I would definitely suggest using Cochrane's formula more, particularly because you have more control over your variabilities, as opposed to Yamanis formula, which is set again and is a derivative of Cochrane's formula, assuming a certain variability. So you could either choose Yamanis formula or Cochrane's formula, and then you can perform for Cochrane's formula, Cochrane's correction. So this would be technically termed as Cochrane's correction for finite populations, because if you notice in Cochrane's formula, you don't necessarily notice the population being considered. So the population is only considered in Cochrane's correction. Okay? And then for both formulas, for Yamanis formula and Cochrane's formula, you could do the response rate correction that we did earlier with a 65% response rate. And then, of course, you have your sample. So very simple, very intuitive, and I hope that it's not that difficult to choose between two formulas that can be used. Um, do take note though that there are some instances where, for example, you're going to do hypothesis testing on a population, and there are other sampling formulas that can be used that would better represent a sample for hypothesis testing. So typically, Amanis and Cochrane's formula are used for descriptive studies where we only want to collect information but not test or compare um, variables or establish causality. Okay, next we have our sampling techniques. For our sampling techniques, we have probability and non-probability sampling. So probability sampling, just to differentiate them, is a sampling techniques where all members of the population has an equal chance to be selected. So meaning that each member of the population can be selected with the same probability, while non-probability sampling is intentional and purposeful. So for this portion, let's start with probability sampling. Now, there are four probability sampling techniques. We have your simple random sampling, you have your systematic sampling, you have your stratified sampling, and you have your cluster sampling. So, your simple random and systematic samplings are the simplest forms of our sampling technique. But then you have your stratified and your cluster sampling that divides the population into groups. For stratified, you refer to them as strata. For cluster, you refer to them as clusters. Okay, so later on, we'll differentiate between the two sampling techniques better. But for now, it's important to remember that the best sampling technique to obtain a representative sample would be your simple random sampling. But also, it might prove to be the most labor intensive. Okay, so let's begin with our simple random sampling. So, our simple random sampling is basically our lottery. Okay, so basically you write the names of your population. This is your population. You write all their names on a list. You cut down that list and then you use a randomizer. In this case, simple random sampling is also known as fishbowl sampling, particularly because you put their names in a fishbowl and then you draw a certain number to meet your minimum required sample size or minimum recommended sample size. And from there, you get your sample. So it's very simple, it's very intuitive, but then it's also very, very labor intensive in a sense that you're going to have to write down all the names of your population and then draw their names. So it might prove to be a bit labor intensive, but otherwise, it's a very good sampling technique to obtain a representative sample. All right. Next, you have your systematic sampling. So, systematic sampling is a bit like your simple random sampling, where you have to write down and list down the names of your respondents. But this time, you're going to have to determine uh, where to start randomly, and then you're going to have to give or determine a number in which to base the system out of. So in this case, we've randomly determined that the first number is 2 and that we're going to get every third member of the population. So what we did was that we randomly identified that we're going to start at number 2 and then every third member of the population is going to be part of the sample. So that would be 1, 2, third, you get number 5 as your sample, and then another 1, 2, 3, and then you get number 8 as your sample, 1, 2, 3, then you get number 11 as your sample, and then And then once you reach the end, you go back to the start. So this would be 1, 2, 3. And then if number 2 has already been selected, you go to the second available number. And then you start again, 1, 2, 3, 1, 2, 3, until of course you fulfill your minimum recommended sample size. So there's not much more to say about systematic sampling, so I'm going to end our uh, discussion about the matter there. But take note, it's also a very good sampling technique to you obtain a representative sample, just like your fishbowl sampling or your simple random sampling. But again, if you're going to go through the trouble of listing down the names of everyone in the population, you might as well just go with simple random sampling. Okay? Next, we have our stratified sampling. So this is one of our probability sampling techniques where the population is divided into groups. In this case, it's called a strata. And then you do random selection within those strata. Okay, so you're going to, let's call this group 1 and you have group 2. So you do random selection from group 1 and group 2. And since you see that group 1 has more members, we've actually taken 4 from group 1 and 3 from group 2. So it's a proportional kind of sampling. You divide them into groups. The larger groups would output more samples, while the smaller groups would output less samples than the larger groups. And we actually use a formula for this to compute for our proportional sample size. So let me just show that to you a bit before we continue with our sampling techniques. Okay. So our stratified sampling formula is just represented by n sub 1, which is the sample size for the first stratum, which we've represented earlier, since in our picture earlier we've divided them into two strata. So n sub 1 is the first stratum, n is the minimum sample size, which we've computed for most likely from Cochrane's formula or Yamana's formula. So either or, as long as we've already computed for the minimum sample size, we use that as n. And then you have the total population at the bottom divided by the total population multiplied by the population of the first stratum. Okay? So it might not be quite as easy to understand this if we don't use it in a problem. So let's have a sample problem. So a sample of 50 students is to be drawn from a population of 500 students belonging to institutions A, which has 200 students, and institution B, which has 300 students. So how many students per institution will be taken as samples for the study? So first, let's identify our variables here. So it says here that a sample of 50 students is to be drawn. So this is our n, small letter n, from a population of 500 students. So this is our big letter N, belonging to institutions A that has 200 students. So this is N sub 1. And institution B, which has 300 students. So this is N big N sub 2. So how many students per institution will be taken as samples for the study? Simply put, simply substitute our variables in the formula. So you have your N over here. You have 500, which is the total population, big letter N, times or multiplied by 200, which is N sub 1. And then you perform the operation, you get 20. Next, for N or sample size of our institution B, simply again use our sample size, which is 50 students. And then you have your 500, which is the population, multiplied by 300, which is your population for institution B. And then you get 30. And if you add them both, you get all the 50 students you need for your sample. Okay? So it's a very simple formula. It's actually just a formula for proportion, and the terminologies were just adjusted to fit sampling. All right? Back to our stratified sampling. So that's basically the first sampling technique, or the first probability sampling technique that uses groups, or that divides the population into groups. And this is particularly useful when um, you want to stratify your sampling. So for example, you're doing medtech students, and the population is very uneven or very unequal for, let's say, first year, second year, third year, and fourth year. So it would be good to stratify your sampling in such a way that, first years have the most population, so you're going to take the most samples from first years, and then second years, third years, and then finally fourth years. So this is to be able to represent each level of the population well, so that you have a sort of more of a normally distributed answer. Okay? So next, we have cluster sampling. So cluster sampling also groups our population into different groups, called, this time we call it clusters. So as you can see, we have a population of about 1, 2, 3, 4, 5, 6, 7 times 5. We have 35 overall in the population. And what we did here was that divide them into groups of 7. Oh, sorry, not 35. So 1, 2, 3, 4, 5, 6, 7 times 10. So that's 70 members of the population. So what we did here was that we divided them into groups of 7. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups of 7 people. And in this case, we're not going to take individuals from each group. No, we're going to be taking the whole group as samples. So in this case, we want to represent about 60% of the population. So, or about 40% of the population. So what we do is that we take cluster 1, cluster 2, cluster 3, and cluster 4. And again, since this is a probability sampling technique, these are all selected in random. That means that we can't intentionally select one cluster to be part of our sampling. Instead, we use a fishbowl technique. So instead of using individual names, we go cluster 1, cluster 2, and then cluster 10. And then we draw from our fishbowl, and then eventually we get our samples. Okay? So that about ends our discussion for probability sampling techniques. Now we move on to non-probability sampling techniques. So this is going to be a bit faster since it's very self-explanatory. It's easier to explain. The concepts are already in the names of our sampling techniques, starting with purposive sampling, where samples are selected based on what is required. Then you have your convenience sampling, excuse me, where the nearest and most accessible samples are taken. You have your quota sampling, which selects sample based on predetermined criteria. And you have your snowball sampling, which is basically a network of samples. Okay, so let's start with purposive sampling. So purposive sampling is a sampling technique where we predetermine what we want to study. Like for example, we're studying a certain disease, let's say diabetic patients, or if we're studying diabetes mellitus type 2, then we're going to have to select members of the population with DM type 2. So we're going to have to first identify if the patient has, or if the person has DM type 2, and then we take them as samples indiscriminately. So what we're actually taking is a member of the population that possesses a certain characteristic or trait of interest, and then we include them in our samples. Okay, so basically that would be purposive sampling, and this is quite useful when we're studying diseases, when we're studying specific traits, when we're studying or testing different interactions for certain medicine, for different interactions of diseases with how society works, and so on and so forth. So, purposive sampling, again, very useful when you want a certain trait to be included in your study. Next, you have your convenience sampling. So convenience sampling is basically, as the as the name suggests, it's basically just taking the most convenient sample, the closest and most accessible person as samples for your research. Now, this is something that does not necessarily provide the best information possible, but sometimes convenience sampling can be used when the characteristics or the criteria for selecting your samples does not necessarily bring any impact or importance on your study. So this is best used when we don't really mind the different characteristics of our population. We just need a member of the population to be part of the sampling frame. Okay? So again, convenient sampling, we take the most convenient sample, the nearest, most accessible. Next, you have quota sampling. So quota sampling is a lot similar to our purposive sampling. So when we say quota sampling, we're trying to set a certain criteria, much like a job selection posting. You have certain qualifications that you have to meet. In this case, it has to be a male who is above 40 years old. And in this case, you have a group of respondents here, and since we only need the males above 40, we're going to take the males who are above 40 years old and no one else. So a lot like purposive sampling, but in this case, it's a more extrinsic, or rather the characteristics are more extrinsic to our respondents. Next, you have snowball sampling. So, snowball sampling is a sampling technique where a researcher, this one in blue, is going to find only one or two respondents for the meantime. So, they're going to find one respondent or two respondents to be part of the research, and then that respondent is going to refer or find more respondents or samples. So this is particularly useful when we're studying sort of sensitive cases of diseases. For example, persons living with HIV, persons with STDs or STIs. So these are diseases, or these are infections that we don't typically want to broadcast to the world. So it's going to be difficult for us to find samples or participants. So what we do is that we find someone we know, or we find someone who we can gain their trust, and then they're going to refer more participants in the study. And then typically these are very discrete kinds of referrals, and so you don't necessarily post on the internet, I am in need of persons who are living with HIV, and so I would like to employ your help in my study. So no one's going to respond to that. So instead, you look for one or two samples or participants, and then you ask them nicely to refer more samples to you. And that's going to be our snowball sampling. Okay? So for our purposes, we've discussed the history of demography. We've discussed the different formulas used in sampling, and we've discussed the different sampling techniques. So, are there any questions? Maybe post it down in the comments, or just give me a message, or just simply find any media you can to ask the questions. There are plenty of references because these are well established concepts already, especially for our sampling techniques. So these are used in almost all fields. So you could literally look for many references and find the different applications that we can use, or we can do, or we can use these sampling techniques for. Okay, so Thank you for listening, and I hope you learned something new. If you have any questions, again, just find any way to contact me, and then I'll try my best to answer your questions. Thank you, and goodbye.